Welcome. Tonight, our journey takes us not into the echoes of the past, but into the profound silence of the future. We will not be tracking the footsteps of dinosaurs or witnessing the birth of ancient seas. Instead, we turn our gaze forward, far beyond the lifespan of human civilization, beyond the rise and fall of continents we know, to a horizon so distant it defies our imagination. We are looking toward the shadows stretching out toward tomorrow, a tomorrow measured not in days or years, but in billions of years. We are traveling to a time when Earth will be ruled by forces far grander and far more indifferent than any volcano or ice age we have explored before. We are journeying to the final, slow, inevitable chapter of our planet's story as a habitable world. We travel to the time of 1 billion years from now. Imagine standing on the Earth in that distant age. It is a world transformed, almost unrecognizable. It is a time when the familiar rhythm of our planet's geological heart is slowing, when the dance of continents grinds towards stillness. It is a time when our most constant and necessary companion, the source of all warmth and light, the sun, begins its slow, patient, and irreversible betrayal. On our voyage tonight, we will witness the planet's final, desperate struggle against its own star. We will explore a world where the vast blue oceans, the cradle of life for nearly 4 billion years, will begin to heat, then to boil, and finally to vanish into the cosmic void, leaving behind immense, gleaming deserts of salt. We will stand by in quiet contemplation as the green kingdom collapses, as the trees and grasses fall silent, their breath stolen by a changing atmosphere. We will see the intricate web of complex life, the animals, the fungi, the life that moves and thinks, dissolve away, replaced by the silent, enduring reign of the simplest organisms, the microbes, returning the planet to a state reminiscent of its earliest, most primitive days. This is not a journey into fantasy, nor a tale of sudden, fiery apocalypse. It is a voyage into deep time, guided by the quiet, inexorable laws of physics that govern stars and planets. It is the story of a slow-motion unraveling, a cosmic certainty written into the life cycle of our sun and the finite heat within our Earth. It is the story of how our blue world will lose its water, its breath, and perhaps even its magnetic shield against the cosmos. It is the story of the long twilight of a habitable planet. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who is joining us from around the world for this journey into the deep future. Now, dim the lights. Maybe turn on a fan for that soft background hum. Perhaps the sound, not of ancient winds, but of the faint, stellar winds of a slowly intensifying sun, a sound crossing the vast expanse of future time. And let's ease into tonight's journey together. The journey into the deep future, to that distant horizon 1 billion years from now, is entirely defined by one single, inescapable cosmic certainty: the slow, patient betrayal of our sun. For 4.5 billion years, our star has been the gentle, stabilizing heart of our solar system, its energy the fundamental source of all life on Earth. We see it as a constant, an unwavering source of light and warmth in our sky. Yet the physics that allow the sun to burn are also the physics that dictate its end, and crucially, the end of our habitable world long before the star itself dies. The sun, even now, as you listen, is not truly constant. It is growing hotter. It is becoming brighter. To understand why, we must look not at its familiar golden surface, but deep into its core, into the unimaginable furnace where the immense pressure and heat, millions of degrees, drive the fundamental reaction of stellar life, nuclear fusion. Here, in this cosmic crucible, hydrogen atoms, the simplest and most abundant element in the universe, are being continuously crushed together under the star's immense gravity. They fuse, transforming into atoms of helium. This process releases the colossal energy that bathes our planet in warmth and light, the energy that powers photosynthesis, drives our weather, and makes liquid water possible. It is the engine of our world. But this engine is also constantly changing its own internal structure, in a way that leads to an inevitable increase in its power output. Imagine the core as a gigantic cosmic furnace, constantly producing helium ash from its hydrogen fuel. As hydrogen is fused, this helium byproduct accumulates in the very center. Helium is denser than hydrogen, and at the current temperatures and pressures within the Sun's core, it cannot yet begin to fuse into heavier elements. It simply sits there, an inert, heavy residue building up over billions of years. This slow accumulation of helium ash is the key to the Sun's quiet, long-term transformation. The growing core of inert helium slowly begins to contract under its own gravity, becoming denser and hotter. This contraction, in turn, increases the pressure and temperature in the surrounding shell of hydrogen, the fuel that is still actively fusing. Think of it like squeezing the active burning layer of the furnace. This increased pressure forces the hydrogen in that shell to fuse even faster, more vigorously. It's a feedback loop inherent in the life cycle of a star like ours. More rapid fusion means more energy is produced deep within the Sun. And more energy produced in the core means the Sun's outer layers, the visible surface we call the photosphere, must expand slightly and radiate that excess energy into space more intensely to maintain equilibrium. The star must become brighter. It must become hotter. It is a slow, almost imperceptible process from our human perspective, but relentless on astronomical timescales. Geologists and astrophysicists, modeling the Sun's evolution based on well-understood stellar physics, estimate that the Sun's total energy output, its luminosity, increases by roughly 1% every 110 million years. Now, project that subtle creeping change across the immense span of our journey tonight. Over the next 1 billion years, that slow 1% increase, compounded 10 times, accumulates into a profound and ultimately catastrophic shift. In 1 billion years, the Sun will be, conservatively, at least 10% brighter and significantly hotter than it is today. This may not sound like an overwhelming change in the vastness of the cosmos, but for the delicate, finely tuned climate system of Earth, it represents the difference between a thriving biosphere and a world pushed beyond the limits of habitability. This 10% increase in the sheer amount of solar energy striking our planet translates directly into a steady, silent, inescapable fever for Earth. The sunlight washing over the future landscapes will be harsher, more intense. The heat absorbed by the atmosphere, the land and the oceans will be significantly greater. Our planet's average global temperature will begin an unstoppable ascent, climbing past the point of comfortable stability that has defined the last few billion years, and eventually crossing critical thresholds that will trigger irreversible planetary-scale failures in the systems that make life possible. This future warming is driven not by geological cycles or atmospheric composition changes originating on Earth itself, but by a fundamental external cosmic certainty, the simple, unavoidable physics of an aging star. It is a process that no force on Earth, no negative feedback loop in the carbon cycle or the biosphere can ultimately stop or reverse. It is a far vaster, slower and more final process than the localized, human-driven warming of our own time. It represents the slow, universal closing of the habitable window for our world. This stellar intensification is the primary engine driving the Earth towards its eventual demise as a living planet. It is the core problem, the inescapable fate that sets in motion the terrifying cascade of events we will explore tonight. forcing the planet to first lose its atmospheric blanket, then its essential carbon dioxide, and finally its vast, life-giving oceans. The Sun, our ancient source of life, begins the long, slow, ultimate process of becoming the agent of our planetary ending. While the Sun, our external source of energy, relentlessly increases its output, setting the stage for the planet's ultimate overheating, another, equally profound transformation is unfolding deep within the Earth itself. A slow, quiet cooling is taking place, a gradual fading of the internal fire that has driven the geological dynamism of our world for billions of years. This inner chill is the second great force shaping the deep future, working in concert with the stellar heat to dismantle the systems that make Earth habitable. We must remember that our planet is not a cold, inert ball of rock. Beneath the thin, cool crust upon which we live lies a vast, slow-churning ocean of molten and semi-molten rock, the mantle, surrounding a core of intensely hot, dense iron and nickel. This internal heat is the legacy of the planet's violent formation, the trapped energy from accretion and impacts, continuously supplemented by the slow, patient decay of radioactive elements like uranium, thorium, and potassium scattered throughout the Earth's interior. This immense reservoir of heat is the engine of our planet's geology. It drives the convection currents within the mantle, those colossal, slow-motion overturnings of hot rock rising and cooler rock sinking. These currents are the unseen hands that push and pull the rigid tectonic plates floating on the surface, driving continental drift, opening ocean basins, and closing them again in fiery collisions that raise mountain ranges. This internal heat also fuels the volcanism that releases gases, including vital carbon dioxide, into the atmosphere, replenishing the air and playing a crucial role in the long-term carbon cycle that regulates our climate. The Earth is geologically alive because it is hot inside, but this internal furnace is not infinite. The primordial heat from formation is constantly, slowly radiating away into the coldness of space. And more significantly, the radioactive elements that act as the planet's internal fuel source are steadily decaying, transforming into stable elements and releasing their stored energy. They are, in effect, running out. As we project forward 1 billion years into the future, the amount of heat being generated deep within the Earth will have significantly decreased. The rate of radioactive decay diminishes over time, following predictable half-lives. The core and mantle will be noticeably cooler than they are today. The planet's internal engine is slowly, quietly losing power. Its geological pulse is weakening. This profound thermal decline has far-reaching consequences. It dictates the long-term fate of the very processes that shape our world's surface. The mantle convection currents, starved of their primary heat source, will become weaker, slower, perhaps more sluggish and less organized. The immense power required to drive the tectonic plates, to push continents apart at mid-ocean ridges, to pull them back down into the mantle at subduction zones, will begin to wane. Imagine the great geological machines slowing down. The restless dance of the continents, which has defined Earth's geography for at least the last 4 billion years, will begin to lose its energy. The movement will become hesitant, perhaps intermittent, before eventually, inevitably, grinding almost to a halt. The era of dynamic plate tectonics, the era that built Pangaea and then tore it apart, the era that continuously reshapes our coastlines and raises new mountains, is drawing towards its close. This internal cooling, this slow geological death, works in a terrifying synergy with the increasing heat from the sun. As the planet loses its ability to regulate its climate through the carbon cycle linked to tectonic activity, it becomes even more vulnerable to the relentless solar warming. And as the internal engine falters, It sets the stage for the failure of another critical planetary system, the very crust itself, which will eventually cease its motion, locking the world into its final, static configuration. The slowing pulse within heralds the coming stillness without. The Earth's inner fire is dimming. The great convection currents stirring the deep mantle, starved of their primordial heat and the dwindling radioactive fuel, are losing their immense planet-shaping power. This internal slowdown translates directly, inevitably, to the surface. The restless dance of the continents, the very engine of geological change that has defined our world for billions of years, begins to falter, stutter, and ultimately cease. Imagine the tectonic plates, those colossal rigid slabs of crust floating upon the weakening mantle currents. Their movement, already imperceptibly slow to us, becomes even slower. The mid-ocean ridges, those vast undersea volcanic chains where new oceanic crust is born, pushing continents apart, receive less heat from below. Their spreading rates diminish. The rate at which the Atlantic Ocean widens or the Pacific shrinks slows to a geological crawl. Simultaneously, the great subduction zones, where old, cold oceanic crust dives back down into the mantle, recycling the planet's surface, begin to seize up. The immense forces required to bend and break the rigid plates, to pull them down against their own buoyancy, are waning. The mantle currents no longer have the strength to maintain this relentless conveyor belt. One by one, over millions, perhaps tens of millions of years, the planet's subduction zones will lock. The downward plunge of oceanic crust will cease. And with the cessation of subduction, the primary engine driving plate movement stops. The Earth's crust, for the first time since its formation perhaps, becomes largely static. The continents, having ground their way towards their final configuration in the supercontinent Pangaea Proxima, will become locked in place, frozen in their ultimate geological embrace. The great planetary waltz ends. The consequences of this geological stillness are profound, touching every aspect of the planet's being. First, the most dramatic and visible signs of geological activity vanish. Volcanism, which requires the melting of rock at subduction zones or mantle plumes, largely ceases. The great volcanic arcs that ring the Pacific, the fiery mountains born from colliding plates, fall silent. The occasional hotspot volcanoes, fueled perhaps by lingering pockets of mantle heat, may flicker for a time, but the planet-wide network of volcanic activity dies out. The Earth stops breathing fire. Mountain building also stops. The immense compressive forces generated by colliding continents, the forces that raised the Himalayas and the Andes, are gone. The existing mountain ranges, including the final colossal chain forged during the creation of Pangaea Proxima, will stand immense and silent, but no new peaks will rise to challenge them. The slow, patient forces of erosion, primarily wind, in this increasingly dry world, will become the only force shaping the landscape, gradually wearing down the existing topography over unimaginable timescales, but with no geological uplift to counteract it. Earthquakes, the sudden, violent release of stress built up along plate boundaries, also fade into silence. With the plates no longer grinding against each other, the source of seismic energy disappears. The planet's crust settles into a profound, almost absolute stillness. But perhaps the most significant consequence for the long-term fate of the atmosphere and climate is the complete breakdown of the Earth's geological carbon cycle. As we saw, plate tectonics acts as the planet's long-term thermostat. Volcanism releases carbon dioxide into the atmosphere, warming the planet. The weathering of silicate rocks, exposed by tectonic uplift, consumes carbon dioxide, cooling the planet. This delicate, slow-motion feedback loop has maintained Earth's climate within a habitable range for billions of years. With the end of plate tectonics, this cycle is broken. Volcanic outgassing essentially stops, cutting off the primary geological source of atmospheric carbon dioxide. Weathering continues, albeit perhaps slowly in the increasingly dry conditions, but with no volcanic replenishment, it acts as a one-way street, potentially drawing down the last vestiges of carbon dioxide from the air. More importantly, the planet loses its ability to respond to long-term changes. It can no longer buffer itself against the increasing heat from the sun by adjusting its atmospheric carbon dioxide levels. The thermostat is definitively, permanently broken. The Earth, 1 billion years from now, is not just hot and dry. It is geologically dead. Its crust is locked. Its internal heat is fading. The vibrant, dynamic, ever-changing world we know has been replaced by a static, silent sphere. Its surface features frozen in time, its atmosphere drifting passively towards its final, sun-driven fate. The locked crust marks the end of Earth's geological life, a profound stillness settling over the planet before the final act of stellar heating begins. Even as the Earth's internal engine sputters and dies, even as the relentless heat from the sun begins its final assault, the continents themselves perform one last, grand and inevitable act in their long geological ballet. Driven by the fading momentum of the mantle currents and the geometry of the existing ocean basins, they complete their slow, inexorable convergence into the planet's final supercontinent, Pangaea Proxima, sometimes called Pangaea Ultima. This is not a sudden event, but the culmination of a process that has been unfolding for the past 200 million years, ever since the breakup of the original Pangaea began. It is the closing act of the current supercontinent cycle. Imagine the world map transforming over the next 250 million years. The Atlantic Ocean, which dramatically split Africa and Europe from the Americas, reaches its maximum width and then begins to shrink. New subduction zones, likely forming along the eastern coasts of North and South America, start to consume the cold, dense Atlantic sea floor, pulling the continents back together like closing a zipper. Simultaneously, Africa continues its slow northward drift, crushing the last remnants of the Mediterranean Sea, the final echo of the ancient Tethys, and colliding more forcefully with Europe, raising immense mountain ranges. Australia, having broken free from Antarctica, drifts northwards, eventually colliding with Southeast Asia, adding its bulk to the growing northern landmass. The final configuration, predicted by geological models based on current plate motions, emerges sometime between 250 and 300 million years from now, long before the sun becomes truly hostile and the oceans fully evaporate. Pangaea Proxima takes shape. It is a vast, sprawling landmass, perhaps centered roughly on the equator, but vastly different in shape from the original Pangaea. Africa has become landlocked, fused at the heart of the new supercontinent, surrounded by South America, Antarctica, Eurasia, and North America. The Americas are joined back to Africa and Europe, closing the Atlantic entirely. What remains of the world's oceans, the Pacific Ocean, the direct descendant of the ancient Panthalassa, becomes even larger, a vast super-Pacific wrapping around more than half the globe. A small isolated ocean basin might remain trapped within the heart of the supercontinent, perhaps a remnant of the Indian Ocean, surrounded on all sides by the converging land masses. This final supercontinent will define the geography of Earth during its last habitable and subsequently uninhabitable stages. Its very existence will profoundly shape the planet's final climate patterns before the ultimate solar heating takes over. Like the original Pangaea, Pangaea Proxima will likely experience extreme continentality. Its vast interior, thousands of kilometers from the moderating influence of the remaining super-Pacific, will become incredibly arid, perhaps forming a new, immense central desert. coastal regions might experience intense, albeit perhaps different, monsoonal patterns. The collision zones that weld the continents together will create colossal mountain ranges, rivaling or even exceeding the Himalayas. Imagine a continuous chain stretching where the Atlantic once flowed, another marking the final closure of the Tethys. These final mountains will stand immense and silent as the planet's geological activity ceases. The formation of Pangaea Proxima is the Earth's geological endgame. It is the final configuration towards which the continents are drifting. It is the stage upon which the last dramas of complex life and the subsequent reign of the microbes will play out. This single, vast landmass, born from the slow closure of today's oceans, represents the ultimate triumph of the internal forces that shape our planet, just before those forces finally fall silent, leaving the world locked in its final geographic form, awaiting the slow, inexorable heat, death delivered by its aging star. The continents have locked into their final embrace, forming the immense static landmass of Pangaea Proxima. The planet's internal heat engine is sputtering, and the restless dance of plate tectonics has ceased, but this internal cooling brings about another, equally profound and insidious consequence: the slow decay and eventual failure of Earth's protective magnetic shield, the magnetosphere. We must remember that our planet is wrapped in an invisible force field, a vast magnetic bubble generated deep within its core. This field extends tens of thousands of kilometers out into space, acting as a vital shield against the constant stream of high-energy charged particles flowing outwards from the Sun, the solar wind, and against damaging cosmic rays originating from deep space. This magnetosphere is not a permanent feature, it is a dynamic consequence of the Earth's internal structure and heat. It is generated by the geodynamo effect. Deep within the planet, the solid inner core sits within a vast ocean of molten iron and nickel, the liquid outer core. The immense heat flowing outwards from the inner core, combined with the Earth's rotation, drives complex churning convection currents within this liquid metal. This motion of conductive fluid acts like a gigantic electrical generator, creating and sustaining the planet's magnetic field. It is a direct product of the Earth being hot, liquid, and spinning in its metallic heart. But as the planet's internal heat diminishes, as the mantle convection slows and plate tectonics cease, the cooling process reaches the core itself. The temperature difference driving the convection currents in the liquid outer core lessens. More significantly, the inner core itself continues to slowly grow as the molten iron at its boundary freezes and solidifies due to the decreasing temperature and immense pressure. Imagine this slow solidification encroaching upon the liquid outer core over hundreds of millions, perhaps billions of years. The volume of churning conductive fluid decreases. The convection currents become weaker, more sluggish. The intricate dance of liquid metal that generates the magnetic field falters. The geodynamo weakens. The magnetic field produced at the surface begins to fluctuate erratically, perhaps undergoing more frequent and prolonged reversals of polarity. Its overall strength diminishes. The protective magnetic bubble surrounding the Earth starts to shrink, becoming less effective at deflecting the incoming solar wind. Eventually, perhaps sometime within the next 1 billion or 2 billion years, the exact timing is uncertain, a critical threshold is crossed. The convection in the outer core becomes too weak to sustain the dynamo effect. The magnetic field collapses, perhaps not instantly, but geologically rapidly, fading away almost entirely. The Earth is left naked, exposed to the harsh realities of interplanetary space. The consequences are dire for the planet's remaining atmosphere. Without the magnetosphere to deflect it, the solar wind, that relentless stream of protons and electrons carrying the Sun's magnetic field, strikes the upper atmosphere directly. This impact acts like a slow, continuous sandblasting process, stripping away atmospheric gases, particularly the lighter elements like hydrogen and helium, and accelerating their escape into space. This process dramatically hastens the loss of any remaining water vapor, ensuring the planet's ultimate desiccation. Heavier gases, like nitrogen and the remaining oxygen or carbon dioxide, are stripped away more slowly, but the process is relentless. The atmosphere, already thin and hot, becomes even thinner over the subsequent eons. Furthermore, the loss of the magnetic shield allows high-energy cosmic rays to penetrate all the way down to the surface, while the sun's own increasing ultraviolet radiation has already rendered the surface sterile for complex life. This influx of cosmic radiation adds another layer of profound hostility, potentially damaging even the most resilient microbial life that might cling to existence in shielded locations. The fading of the magnetic field is another silent, invisible marker of the planet's slow death. It is the loss of Earth's cosmic armor, a consequence of its cooling heart. The stillness that has fallen upon the continents now extends outwards into the space surrounding the planet. The Earth becomes a passive, vulnerable sphere, increasingly at the mercy of its aging star and the harsh environment of the solar system. The protective silence of the magnetosphere is replaced by the silent, erosive whisper of the solar wind. While the Earth itself undergoes profound internal and atmospheric transformations, its heart cooling, its oceans vanishing, its shield fading, another, equally constant yet perhaps more subtle drama plays out in the space immediately around us. Our nearest celestial neighbor, the Moon, our constant companion in the night sky for billions of years, is slowly, silently drifting away. This cosmic separation is not a dramatic event, but a quiet, inevitable consequence of the gravitational dance between the Earth and its satellite, a dance mediated by the very oceans that are now beginning their long retreat. We must remember how tides work. The Moon's gravity pulls on the Earth, creating a subtle bulge not just in the oceans, but in the solid rock itself. As the Earth rotates rapidly beneath this bulge, the friction between the moving water, primarily, and the seabed acts as a brake, ever so slightly slowing the planet's spin. But Newton's third law dictates that for every action, there is an equal and opposite reaction. The energy lost by the Earth's slowing rotation must go somewhere. It is transferred through the intricate push and pull of gravity to the Moon. This tiny, continuous transfer of angular momentum gives the Moon a slight boost in its orbit. It accelerates it just a fraction, causing it to spiral slowly outwards, away from the Earth. In our own time, we can measure this recession with incredible precision using lasers bounced off reflectors left on the lunar surface by the Apollo missions. The Moon is moving away from us at a rate of approximately 3.8 centimeters, about 1.5 inches per year, the width of your fingernail. This seems infinitesimal, utterly negligible on human timescales. But project this slow, patient drift across the vast expanse of 1 billion years. The distance accumulates. Imagine the night sky 1 billion years from now. The familiar constellations will have shifted slightly due to the slow drift of stars, but the most noticeable change will be the Moon itself. It will appear visibly smaller in the sky, its apparent diameter reduced because it is significantly farther away. Its gravitational influence, its comforting, familiar presence, will feel diminished. The consequences of this gradual separation ripple back to Earth, profoundly altering the planet's rhythm and character, even in its increasingly dry state. Most obviously, the tides, which have defined the rhythm of Earth's coastlines for eons, will weaken considerably. As the Moon moves farther away, its gravitational pull lessens proportionally. the tidal bulges raised on the remaining hypersaline brine pools, or perhaps just within the solid body of the Earth itself, will become much smaller. The dramatic rise and fall of the sea, the constant mixing and churning of coastal waters that played such a vital role in the evolution of early life, will fade into a mere whisper, a faint echo of its former power. The planet loses its oceanic heartbeat. Simultaneously, the Earth's rotation continues to slow. The constant braking effect of the tides, though weakening as the moon recedes and the oceans vanish, has been acting for billions of years. The length of a day, which was perhaps only a few hours long shortly after the Earth formed, has already lengthened to our familiar 24 hours. This process continues. 1 billion years from now, the Earth's day will be significantly longer than it is today, perhaps approaching 27 or 28 hours. The slow, languid rhythm of sunrise and sunset will stretch out, altering the daily temperature cycles on the already heat-stressed surface. But perhaps the most profound long-term consequence of the moon's receding dance lies in its role as Earth's stabilizer. Our moon is unusually large compared to its parent planet, and its gravitational influence acts like a steadying hand on Earth's rotational axis. It keeps our axial tilt, the 23.5-degree angle that gives us predictable seasons, remarkably stable over long geological timescales. As the moon drifts farther away, this stabilizing grip weakens, while the truly chaotic variations in axial tilt, potentially swinging the planet wildly between 0 and 90 degrees, may lie further in the future, perhaps 1.5 to 4.5 billion years from now. The process of destabilization begins long before. The slow recession of the moon is gradually loosening the gyroscopic lock that has blessed Earth with relatively stable climates for so long. The Earth of 1 billion years hence is a planet becoming increasingly untethered from its celestial anchor. Its days are longer, its tides are weaker, and its rotational stability, the very foundation of predictable seasons, is slowly eroding. The moon continues its quiet, outward spiral, a constant visible reminder in the future sky of the slow, inexorable unwinding of the planetary system, a dance leading towards a future of even greater cosmic uncertainty and environmental hostility. The familiar celestial clockwork is slowly, silently coming undone. The moon recedes, its gravitational grip loosening, its familiar face shrinking in the deep future sky. The Earth's own heart cools, its geological pulse fading towards silence. These are profound changes, reshaping our planet's rhythm and structure over immense timescales. But they are secondary players in the final act. The true driver of Earth's ultimate fate, the inescapable force dictating the end of habitability, remains the star at the center of our system, the Sun. We return now to that fundamental cosmic certainty, the slow, inexorable increase in the Sun's luminosity. We established earlier the mechanism, the buildup of helium ash in the core, forcing the surrounding hydrogen shell to fuse faster, causing the star to burn brighter. And we noted the estimated rate, approximately a 1% increase in brightness every 110 million years. Now, let us place ourselves precisely at that distant milestone. 1 billion years from today. 10 cycles of that slow, stellar brightening have passed. The Sun, hanging in the sky of this future Earth, is now radiating approximately 10% more energy than the star we know. 10%! It sounds modest perhaps in the grand scale of the cosmos, but for a planet like Earth, orbiting within the delicate habitable zone, this is a catastrophic increase. This is the stellar tipping point that unravels the intricate systems that have maintained liquid water and complex life for billions of years. Imagine the sunlight falling on the dry, static surface of Pangaea Proxima. It is harsher, more intense. The quality of the light itself might seem different, perhaps whiter, less golden. The energy striking every square meter of the planet, every second, is significantly greater. This relentless influx of additional energy overwhelms the planet's already crippled ability to regulate its temperature. The geological carbon cycle, the great thermostat involving plate tectonics and rock weathering, has effectively shut down. The biological carbon cycle, driven by photosynthesis, collapsed hundreds of millions of years earlier with the extinction of plant life. There are no remaining planetary-scale mechanisms to counteract this stellar heating. The Earth can only absorb and attempt to radiate the heat back into space. But the atmosphere, even in its thin, dry state, still contains gases that trap some of that outgoing heat. The greenhouse effect persists, perhaps even amplified initially by the immense volumes of water vapor released during the ocean evaporation phase, before that water was ultimately lost to space. The consequence is a dramatic, sustained rise in global average surface temperature. While the path to this point involved complex feedbacks, crossing the 10% luminosity threshold pushes the Earth firmly into a new, stable, but utterly uninhabitable climate state. The average temperature settles at the searing level we anticipated, perhaps 70 degrees Celsius, 160 degrees Fahrenheit, or even higher. This is not a temporary heat wave, it is the new normal, a permanent planet-wide condition dictated by the sun's output. Picture the world under this constant oppressive heat. The vast salt flats, remnants of the evaporated oceans, shimmer endlessly under the fierce sunlight. The ancient eroded mountain ranges of Pangaea Proxima bake, their rocks expanding and contracting in the extreme, though perhaps less dramatic daily temperature swings now moderated slightly by the thicker, heat-retaining, though dry atmosphere. There is no shade, no coolness, no refuge. The very air itself is a suffocating blanket of heat. Even the nights offer little respite as the atmosphere retains the day's immense thermal load. This intense, inescapable heat is the ultimate barrier to complex life. No animal, no plant, no fungus as we know them could possibly survive, let alone evolve, in such conditions. Their delicate cellular machinery, their proteins and enzymes, would simply cook, denature, and cease to function. The 10% brighter sun marks the definitive endpoint for Earth as a potentially habitable world in any recognizable sense. It drives the evaporation of the oceans. It ensures the sterilization of the surface through heat alone, even without considering the increased ultraviolet radiation. It transforms the planet from a complex, dynamic, living system into a simple, static, heat-death victim. This stellar milestone, reached 1 billion years from now, is the quiet, cosmic checkmate. The Earth has lost its internal dynamism, lost its water, lost its shield, and now its star, the very source of its former vitality, has become the agent of its final, permanent desolation. The stage is set for the slow, final unwinding, the loss of the atmosphere itself, and the long wait for the sun's ultimate expansion, billions of years further down the road. The sun burns 10% brighter, its relentless energy pouring down onto a geologically silent, static Earth. The planet's average temperature has climbed, settling into a searing equilibrium around 70 degrees Celsius. This profound, inescapable heat now triggers the first stage of the final dismantling of Earth's defining feature, its vast, blue oceans. This is the beginning of the moist greenhouse phase, the precursor to the complete loss of our world's water. Imagine the surface of the remaining oceans, or perhaps the vast, hypersaline lakes that are the final remnants of the seas. Under the intense solar radiation and the oppressive atmospheric heat, the rate of evaporation accelerates dramatically. Water molecules, energized by the heat, leap from the liquid surface into the air at an ever-increasing rate. The lower atmosphere, the troposphere where our weather occurs, becomes saturated with water vapor. Humidity climbs to levels unimaginable in our current climate. The air becomes thick, heavy, almost viscous with moisture. Visibility would likely decrease, the world perpetually shrouded in a dense, hot haze or fog. Crucially, water vapor itself is the most potent greenhouse gas in our atmosphere. While carbon dioxide sets the long-term thermostat, water vapor acts as a powerful amplifier. As more water evaporates into the hot air, this dense blanket of atmospheric moisture traps even more of the heat radiating upwards from the planet's surface. This creates a powerful positive feedback loop, a runaway cycle of heating and evaporation. The sun heats the surface water evaporates. The water vapor traps more heat. The trapped heat further warms the surface, causing even more water to evaporate. The planet is essentially sweating under its stellar fever, and that sweat, the water vapor itself, acts like wrapping itself in ever thicker, heavier blankets, making the fever worse. This stage is called the moist greenhouse, because while the atmosphere becomes incredibly laden with water vapor, the oceans themselves have not yet reached a true violent boiling point across their entire surface. Liquid water still exists, perhaps vast, albeit shrinking, bodies of it. But the rate at which that water is being transferred into the atmosphere is accelerating exponentially. The air itself becomes a significant reservoir of the planet's water, holding a far greater percentage of the total H2O than it does today. This atmospheric burden of moisture further increases the surface pressure, making the air feel even heavier, more oppressive. This intense evaporation has consequences beyond just the heat and humidity. It likely drives extreme, though perhaps infrequent, weather patterns. Imagine colossal, slow-moving storms, born from the superheated, moisture-laden air, potentially dumping torrential, though incredibly hot, rain in localized areas before the water rapidly evaporates again. The hydrological cycle becomes hyper-accelerated but increasingly inefficient at retaining water on the surface. This period marks the beginning of the end for liquid water as a stable, dominant feature of the Earth's surface. The oceans are no longer vast, stable reservoirs, but are actively, visibly losing their substance to the atmosphere at an alarming rate. The equilibrium has been broken. The planet has crossed a threshold where the atmospheric escape route for water, previously a slow trickle, is about to become a floodgate. The air is thick with the ghost of the oceans, a prelude to their final departure into the void. The moist greenhouse is the atmosphere's final, desperate attempt to hold on to the water, an attempt that is doomed to fail as the process reaches into the highest layers of the sky. The lower atmosphere is now saturated, a thick, heavy blanket of superheated water vapor driven off the shrinking oceans by the relentless solar heat. The moist greenhouse is in full effect. But for the planet to truly lose its water forever, this vapor must find a pathway out, a route beyond the grasp of Earth's gravity. That pathway lies high above, through a normally impassable barrier, the stratospheric cold trap. Let us picture the structure of our atmosphere as it exists today, and for most of Earth's history. As we ascend from the surface, the temperature generally decreases through the troposphere, the layer where our weather occurs. But then, at an altitude of around 10 to 15 kilometers, something crucial happens. The temperature stops falling and begins to rise again as we enter the stratosphere. This boundary layer, the tropopause, where the temperature is at its minimum, perhaps minus 60 degrees Celsius or colder, acts as an incredibly effective barrier for water vapor. Think of it as a natural freeze dryer for the air rising from below. As warm, moist air ascends, it cools. When it reaches the frigid temperatures of the tropopause, almost all of the water vapor condenses out, forming ice crystals that eventually fall back down as precipitation. Only an incredibly tiny fraction of water molecules, in vapor form, manage to pass through this intense cold trap and enter the dry, stable stratosphere above. This mechanism is fundamentally why our upper atmosphere is so remarkably dry, and why our planet has been able to hold on to its vast oceans for billions of years. The cold trap acts as a planetary seal, keeping the water locked within the lower, circulating part of the atmosphere. But in the world of 1 billion years from now, under the immense thermal load of the 10% brighter sun, this vital seal begins to fail. The sheer amount of heat radiating from the superheated surface, combined with the massive quantity of water vapor being pumped into the lower atmosphere, fundamentally alters the atmospheric structure. The troposphere warms and expands upwards. Crucially, the tropopause itself, that coldest point in the atmospheric profile, becomes warmer and is pushed to higher altitudes. Imagine that freeze dryer becoming less efficient, less cold. As the tropopause warms, its ability to force water vapor to condense and precipitate out diminishes significantly. More and more water molecules, carried upwards by powerful convective currents in the superheated, moisture-laden lower atmosphere, are now able to push through this weakened cold trap. For the first time on a planetary scale, significant quantities of water vapor begin to infiltrate the stratosphere. This layer, normally characterized by its extreme dryness, starts to become humid, moist. This stratospheric moistening is the critical, irreversible turning point in the story of Earth's water. It represents the breaching of the planetary dam. Once water vapor reaches these high altitudes, typically above 50 kilometers, it is no longer protected. It enters a realm where it is directly exposed to the harshest, most energetic components of the sun's radiation, the hard ultraviolet light. This is the escape route. The leak has begun. The cold trap, which faithfully guarded Earth's water for eons, has been overwhelmed by the sheer thermal violence of the aging sun. Water vapor, the very essence of our blue planet, is now pouring upwards into the high atmosphere, reaching the altitudes where it will be irrevocably dismantled and lost forever to the void. The slow, silent hemorrhage of the oceans into space has truly begun. The sky itself has become the conduit for the planet's final dehydration. The seal is broken. The weakened cold trap can no longer hold back the immense flood of water vapor rising from the superheated oceans below. Significant quantities of H2O molecules, the fundamental substance of life and oceans, are now reaching the high stratosphere and even the layers above, perhaps 50, 60, or even hundreds of kilometers above the surface. Up here, the atmosphere is incredibly thin, almost a vacuum by terrestrial standards, and up here there is no protection. The lower atmosphere, even in its dense, hot state, still filters out some of the most damaging components of solar radiation. But in these high, tenuous reaches, the sun's full, unfiltered fury reigns. Specifically, the water molecules are now directly exposed to the high-energy ultraviolet radiation streaming constantly from our star. This ultraviolet light, particularly the shorter wavelengths known as UVC and extreme UV, carries enough energy to act like a microscopic knife, slicing apart the very chemical bonds that hold water molecules together. This process is called photolysis or photodissociation, light breaking things apart. Imagine a single water molecule composed of one oxygen atom bonded to two hydrogen atoms, drifting in the thin, high atmosphere. It is struck by an incoming high-energy ultraviolet photon from the sun. The energy of that photon is absorbed by the molecule, not just warming it, but violently shaking its internal structure. The chemical bonds, the shared electrons holding the atoms together, are overwhelmed. They snap. The water molecule disintegrates. It breaks apart into its constituent fragments. Often, it splits into a highly reactive hydroxyl radical, an oxygen atom still bonded to one hydrogen atom, OH, and a lone free hydrogen atom, H. Sometimes the dissociation is even more complete, breaking the molecule directly into a free oxygen atom and 2 free hydrogen atoms. This process happens continuously, relentlessly, wherever water vapor meets unfiltered sunlight in the upper atmosphere. Billions upon billions of water molecules newly arrived from the failing cold trap below are subjected to this constant ultraviolet bombardment. The upper atmosphere becomes a vast chemical battlefield where the sun's energy systematically dismantles the very essence of Earth's oceans. The oxygen atoms and hydroxyl radicals produced by this photolysis are highly reactive. They might recombine with each other, perhaps forming molecular oxygen, O2, or even trace amounts of ozone, O3, though the overall conditions are likely too harsh and the concentrations too low for a stable ozone layer to reform effectively. They might react with other atmospheric gases, contributing to the complex evolving chemistry of this strange, hot upper atmosphere. But the fate of the hydrogen atoms is far simpler and far more final. Hydrogen is the lightest element in the universe, a single proton. Once freed from the water molecule by the ultraviolet knife, these hydrogen atoms possess very little mass. In the high temperatures of the upper atmosphere, they are moving incredibly fast, energized by the same solar radiation that broke them free. At these altitudes, the Earth's gravitational pull is significantly weaker, and for these light, fast-moving hydrogen atoms, the escape velocity, the minimum speed needed to break free from the planet's gravitational grasp entirely, is easily achieved. They simply drift upwards and outwards, propelled by thermal energy and perhaps pushed by the pressure of the solar wind, now penetrating deeper due to the weakened magnetic field. They leave the thin outer fringes of the atmosphere behind. They enter interplanetary space. They are gone forever. This is the ultimate irreversible step in the loss of Earth's water. Photolysis, driven by the sun's intensifying ultraviolet output, acts as the planetary disassembly line. It takes the water vapor delivered from the oceans below, breaks it into its fundamental components, and then allows the crucial hydrogen component to escape into the cosmic void. The oxygen is left behind, perhaps, but the water itself is permanently destroyed, its hydrogen lost to the solar system. The ultraviolet knife is relentlessly carving away the planet's hydrosphere, ensuring that the water leaving the oceans does not simply cycle back as rain, but embarks on a one-way journey into space. The scale of this loss, driven by the moist greenhouse and the physics of photolysis, is immense, guaranteeing the eventual complete desiccation of the planet. The ultraviolet knife of the sun slices relentlessly through the water molecules that have breached the stratosphere. High above the scorching surface, in the thin, exposed upper reaches of the atmosphere, the very substance of Earth's oceans is being chemically dismantled. Water is broken into fragments, oxygen atoms, reactive hydroxyl radicals, and, crucially, free hydrogen atoms. The fate of the oxygen and hydroxyl is complex. They might react, recombine, linger. But the fate of the hydrogen is brutally simple. It escapes. Hydrogen is the lightest of all elements. A single proton, perhaps bound with a single electron. Once freed from the water molecule by photolysis, these individual hydrogen atoms are incredibly lightweight particles, possessing minimal mass. In the extreme environment of the upper atmosphere, the thermosphere and exosphere, temperatures are paradoxically very high, not in the sense of heat we would feel, the gas is too thin, but in the sense that the individual atoms and molecules are moving extremely fast, energized by the absorption of high-energy solar radiation. These liberated hydrogen atoms, possessing little inertia, are easily accelerated to tremendous speeds. And at these altitudes, hundreds or thousands of kilometers above the surface, the Earth's gravitational pull is significantly weaker than it is down here. closer to the planet's center of mass. The force holding the atmosphere captive diminishes with distance. For these light, fast-moving hydrogen atoms, the combination of high thermal velocity and weakening gravity means they frequently, easily achieve escape velocity. This is the critical speed, about 11 kilometers per second near the surface, but lower at higher altitudes, needed for an object, or in this case an atom, to break free from the planet's gravitational grasp entirely and enter interplanetary space. Imagine these individual hydrogen atoms, energized by the sun, zipping through the tenuous outer fringes of the atmosphere. Many will collide with other particles, perhaps be briefly recaptured. But many others, on an upward trajectory, will simply reach a speed and altitude where Earth's gravity can no longer hold them. They drift upwards and outwards, propelled by thermal energy, perhaps nudged further by the constant pressure of the solar wind, that stream of charged particles flowing from the sun, which now penetrates deeper into the atmosphere due to the likely weakened or absent magnetic field. They cross the invisible boundary where Earth's influence ends and interplanetary space begins. They join the thin solar wind itself, becoming part of the tenuous gas that fills the void between the planets. They are swept away, lost to the solar system. This process is called atmospheric escape, or more specifically for hydrogen, hydrodynamic escape. And it is utterly irreversible. Unlike the water cycle we know, evaporation, condensation, precipitation, where water changes form but remains within the Earth system, this escape is a one-way street. The hydrogen atoms lost to space do not return. They cannot be recaptured. The planet's inventory of this fundamental building block of water is being permanently depleted. This is the ultimate mechanism by which Earth loses its oceans. It is not simply boiling them away into the atmosphere. It is chemically dismantling them high above and allowing their most crucial component, the hydrogen, to bleed silently, continuously into the cosmic void. Picture the planet over millions, tens of millions, hundreds of millions of years. A slow, invisible hemorrhage occurring at the very top of the atmosphere. While the surface world roasts and the last brine pools shrink, the sky itself is facilitating the planet's final dehydration. Every water molecule broken apart, every hydrogen atom escaping, brings the end of the blue planet one infinitesimal step closer. The scale of this loss, driven relentlessly by the brightening sun, is immense, guaranteeing the eventual complete desiccation of the world, leaving behind only the heavier oxygen, perhaps, and the dry, rocky, salty bones of the planet itself. The escape of hydrogen is the final quiet signature of an ocean evaporating not just into the air, but into the infinite emptiness of space. The hydrogen bleeds away, an invisible, irreversible hemorrhage at the top of the atmosphere. The water molecules, broken by sunlight, give up their essence to the void. Down below, on the scorching surface of the Earth 1 billion years from now, the consequences of this slow, cosmic drain become starkly, dramatically visible. The great oceans begin to retreat. This is not the familiar ebb and flow of tides, nor the slow rise and fall of sea levels driven by ice ages or tectonic shifts. This is a fundamental, one-way decline. The total volume of liquid water on the planet is decreasing, year after patient year, millennium after millennium. Imagine standing on what was once a coastline, perhaps the familiar edge of a continent we know today. The sound of waves crashing, the smell of salt spray, the cool, moist breeze. These are memories billions of years old. Now the shoreline is far in the distance, a hazy line perhaps tens, even hundreds of kilometers away across a newly exposed barren plain. As the oceans lose their water to the atmospheric escape route, the global sea level falls. Not by meters, as in our ice ages, but by kilometers. Relentlessly. The first lands to emerge are the vast, shallow continental shelves, those underwater extensions of the continents that gently slope away from the current coastlines. In our world, these shelves are vibrant ecosystems teeming with coral reefs, kelp forests, and fisheries. In the deep future, baked by the intense sun and bathed in hypersaline waters before the final evaporation, they become something else entirely. Picture these immense plains emerging from the receding waters. They are flat, vast, perhaps initially covered in thick layers of mud and marine sediment deposited over eons. But under the searing heat and dry air, this mud quickly dries, cracks, and perhaps blows away as dust, revealing the underlying rock or vast expanses of salt left behind by the evaporating seawater. These new coastlines are not beaches of sand and gentle waves, but stark, sterile boundaries between the shrinking brine and the expanding, sun-baked land. The geography of the world transforms. Archipelagos merge into larger landmasses as the shallow seas between them disappear. Inland seas, like perhaps the remnant of the Tethys trapped within Pangaea Proxima, shrink and vanish, leaving behind immense salt-encrusted basins deep within the supercontinent. The very shape of the continents, defined for so long by their watery edges, becomes sharper, more angular, as the lower slopes of the continental margins are revealed. The world map is being redrawn by subtraction, the blue areas shrinking relentlessly, the brown and white areas expanding. The process accelerates as the feedback loops intensify. Less ocean surface means slightly less water vapor entering the atmosphere overall, though the rate of evaporation from the remaining water is extreme. But the sun's heat continues to increase, driving the atmospheric escape process ever faster. The remaining water bodies become increasingly concentrated, increasingly saline, accelerating the demise of any lingering marine microbial life. Imagine the view from space now. The familiar blue marble is fading. The oceans are no longer vast, interconnected bodies dominating the globe. They are shrinking patches of perhaps reddish or orange brine, confined to the deepest parts of the old ocean basins, surrounded by immense, dazzlingly white salt flats and the dull ochre expanse of the dry land. The emergence of these new coastlines is not a sign of new beginnings, but a marker of profound loss. It is the planet revealing its bones as its lifeblood evaporates. Each meter of falling sea level, each square kilometer of newly exposed land, is another step towards the final, inevitable state of a dry, sterile world. The receding oceans are writing the final chapter of Earth's 4 billion-year history as a water world, leaving behind a landscape utterly alien to anything we have ever known. The oceans retreat, their blue essence bled away into the cosmos, leaving behind not fertile plains, but a new geological empire defined by absence. As the water vanishes, the minerals that were dissolved within it for billions of years remain, precipitating out of the final hyper-concentrated brines to form colossal, planet-spanning salt flats. This is the great global salt pan, the defining landscape of the desiccated Earth. Let us try to visualize this utterly alien world, perhaps standing in the heart of what was once the deep Pacific Basin. A billion years from now, the familiar landmarks are gone. The water is gone. Instead, stretching to the horizon in every direction, is a vast, flat, and blindingly white expanse. This is not snow or ice, this is salt. Primarily sodium chloride, common table salt, but mixed with vast quantities of other evaporate minerals, gypsum, anhydrite, potassium salts, magnesium salts. Layer upon layer precipitated out over millennia as the oceans dwindled, these minerals have formed deposits of almost unimaginable thickness. In the deepest parts of the former ocean basins, these salt layers might be hundreds, even thousands, of meters thick, burying the ancient abyssal plains and mid-ocean ridges beneath a monumental crystalline crust. Imagine the scale. Not the Bonneville salt flats, not the Salar de Uyuni, but formations covering areas larger than continents, gleaming white under the fierce, unfiltered sunlight of the hotter sun. The sheer reflectivity, the albedo, of these immense salt plains would be enormous, bouncing a significant fraction of the incoming solar energy back into space, perhaps creating complex, localized atmospheric effects, but doing little to cool the planet overall against the overwhelming solar output. The surface of these salt flats would be sculpted by the harsh, dry wind, the only remaining agent of erosion in this waterless world. Perhaps vast fields of salt dunes march slowly across the plains. Perhaps intricate razor-sharp ridges and crystalline formations known as salt karst or salt polygons form through slow processes of dissolution and recrystallization, driven by the minimal atmospheric moisture and extreme temperature swings between day and night. The air above these salt flats would be thick, hot, and punishingly dry, though perhaps carrying a fine, abrasive dust of salt crystals lifted by the wind. The silence would be profound, broken only by the whisper of that wind, and perhaps the sharp cracking sound of the salt crust expanding and contracting under the thermal stress. What was once the dynamic, life-filled ocean floor is now a static, sterile, geological monument, a testament to the sheer volume of dissolved minerals the oceans once held, now laid bare. These salt deposits are not merely a surface feature. They represent a fundamental chemical shift in the planet's geology. They lock away vast quantities of chlorine, sodium, sulfur, and other elements, removing them from any potential atmospheric or biological cycles forever. They are the final, inert residue of the planetary water cycle. Life, as we know it, cannot exist here. The extreme salinity, combined with the intense heat and radiation, makes these salt flats among the most hostile environments imaginable, even for extremophile microbes. Perhaps only within deep brine pockets trapped within the salt layers, shielded from the surface conditions, could the most resilient haloarchaea possibly endure in a state of near-permanent dormancy. To traverse this empire of salt would be to cross a landscape of blinding geometric beauty, but also one of profound final desolation. It is the color of absence. It is the texture of sterility. It is the ultimate geological signature of a planet that has lost its oceans, leaving behind only the crystalline ghosts of the water that once defined it. The blue marble has become a white crystal ball, reflecting the harsh light of its dying star. Even within the vast emerging empire of salt, the final act of the ocean's demise unfolds not instantaneously, but through a slow, lingering phase where the last vestiges of liquid water persist. Before the planet becomes utterly, irrevocably dry, there exists a period defined by the final remnants of the seas, the hypersaline lakes. Imagine these final water bodies, scattered perhaps across the deepest depressions of the ancient ocean basins, nestled within the immense, blinding expanse of the salt flats. These are not the vast blue oceans of Earth's prime, nor even the shrinking brine seas of the early evaporation phase. These are the dregs, the final, concentrated essence of the hydrosphere. Their size diminishes relentlessly as the atmospheric escape of hydrogen continues. What might have started as significant, albeit shallow, inland seas within the salt plains shrink over millennia into lakes, then ponds, then ephemeral puddles, clinging precariously to existence under the ever-intensifying solar glare. Their chemistry is extreme beyond comprehension. As pure water preferentially evaporates, the dissolved salts become ever more concentrated. These are not merely salty lakes. They are hypersaline brines, far exceeding the salinity of the Dead Sea or any natural water body on Earth today. The water is thick, viscous, almost syrupy with dissolved minerals. Its freezing point is far below zero, and its boiling point significantly elevated by the immense concentration of solutes and the high atmospheric pressure. Yet, somehow, paradoxically, they remain liquid, at least for a time, even under surface temperatures approaching or exceeding the normal boiling point of water. The sheer concentration of salts acts as a potent antifreeze and anti-boil agent, allowing these liquids to persist in a state utterly alien to our experience. Imagine looking out across one of these final lakes. The water is likely not blue, but stained deep, impossible colors, vibrant reds, oranges, purples, perhaps even greens, by the only forms of life capable of enduring such conditions. These are the extreme halophiles, primarily archaea, ancient single-celled organisms that have evolved biochemical mechanisms to thrive in environments saturated with salt. Their pigments, used perhaps for protection against the intense solar radiation or as part of unique metabolic pathways, paint the last waterscapes in lurid, almost psychedelic hues. The shores of these lakes are not gentle slopes, but likely sharp, crystalline banks of precipitating salt, constantly growing inwards as the water level drops. The air above is thick, shimmering with heat, heavy with the caustic smell of evaporating brine, and perhaps the faint, strange metabolic byproducts of the extremophile life within. These hypersaline lakes represent the absolute final refuge for surface aquatic life. No fish, no crustaceans, no complex algae could survive here. The environment is simply too toxic, too chemically demanding. Only these specialized microbes, perhaps descendants of lineages that have inhabited salt flats and brine pools for billions of years, can withstand the osmotic stress, the chemical bombardment, and the intense heat. They form thick, perhaps slimy, microbial mats around the edges and on the bottom of these lakes, engaging perhaps in strange forms of photosynthesis adapted to the extreme conditions, or chemosynthesis, drawing energy from the bizarre inorganic chemistry of the brine itself. These microbial communities are the last ecosystems on the surface of the Earth, incredibly simple, slow-growing, and existing at the very edge of physical possibility. But even these ultimate survivors are living on borrowed time. The water continues to evaporate. The hydrogen continues to escape into space. The lakes shrink, become even more concentrated, hotter, more viscous. Eventually, one by one, they reach their final limit. The last pockets of liquid water vaporize completely, leaving behind only layered, perhaps beautifully colored, deposits of salt and the desiccated, dormant spores of the microbes that once inhabited them. The era of hypersaline lakes is the final, lingering sigh of the Earth's oceans. It is a period of beautiful, toxic, and ultimately doomed extremity. When the last of these colorful brine pools finally dries, the 4 billion-year reign of liquid water on the surface of our planet comes to its definitive, silent end. The last drops have vanished. The world is now truly dry. The last drops of surface water have vanished, leaving behind an empire of salt beneath a scorching, hazy sky. The planet is dry, but the catastrophe driven by the intensifying sun unfolds not just through the loss of water, but through a simultaneous, equally devastating attack on the very air itself, specifically targeting the trace gas that forms the fundamental building block of all complex life: carbon dioxide. We must return for a moment to the delicate planetary thermostat, the silicate weathering feedback, which played such a crucial role earlier in our journey. Remember how rising temperatures accelerate the chemical breakdown of rocks on land, a process that consumes carbon dioxide from the atmosphere, locking it away in ocean sediments. For billions of years, this mechanism acted as Earth's great stabilizer, preventing runaway heating or freezing. But under the relentless 10% increase in solar luminosity, this stabilizing feedback becomes a fatal flaw. The planetary system, desperately trying to cool itself against the sun's onslaught, drives the weathering process into overdrive. The intense heat and perhaps initially increased humidity before the oceans fully vanished, dramatically accelerate the chemical reactions that pull carbon dioxide from the air. Meanwhile, the geological sources that replenish atmospheric carbon dioxide, primarily volcanic outgassing, have dwindled to almost nothing with the cessation of plate tectonics. Carbon dioxide is being vigorously scrubbed from the atmosphere, but it is not being replaced. The concentration of this vital gas, already perhaps low following the peak of the moist greenhouse, begins a final, catastrophic decline. It falls below the levels required to sustain the engines of life. The first victims are the plants we know best, the C3 photosynthesizers. This group includes almost all trees, shrubs, and the majority of the world's food crops. Their method of capturing carbon dioxide from the air is relatively inefficient, requiring a certain minimum concentration to function effectively. As atmospheric carbon dioxide levels drop, sometime perhaps between 500 and 900 million years from now, they reach this critical threshold, the compensation point. Below this point, C3 plants simply cannot take in enough carbon to build their tissues and power their metabolism. They begin, in effect, to starve, unable to draw sustenance from the thin air. Imagine the great forests that might have clung to existence in the slightly cooler polar regions or high mountain refuges during the initial warming phase. Now, they face a silent, invisible famine. Their leaves yellow, growth ceases, and one by one they wither and die, not from lack of water, which is also becoming critical, but from lack of atmospheric food. The vast, complex ecosystems built around C3 plants collapse completely. For a time, perhaps another 100 million years or so, the more resilient C4 plants, the grasses, maize, sugarcane, plants biochemically adapted to concentrate carbon dioxide, inherit the earth. They form the vast, monotonous savannas that represent the last stand of the Green Kingdom. But even their sophisticated metabolic machinery cannot fight the relentless decline forever. As weathering continues its inexorable work, the atmospheric carbon dioxide concentration falls even further, eventually dropping below the compensation point, even for C4 photosynthesis. This marks the definitive end of plant life on Earth. The last grasses wither, the final pockets of green vanish from the landscape. The planet, which had been painted in shades of blue and green for billions of years, now settles into its final palette of reds, oranges, browns, and the stark, sterile white of the salt flats. The silence that falls is profound. It is not just the absence of animal calls, but the cessation of the wind rustling through leaves, the end of the slow, patient breath of photosynthesis that sustained the entire complex biosphere. The primary producers are gone. The base of the food web has crumbled, and for the creatures that depended entirely upon them, the animals, the final curtain call is now unavoidable. The stage is set for the extinction of the animal kingdom itself. The green world is gone. Carbon dioxide, scrubbed from the atmosphere by the planet's malfunctioning thermostat, has fallen below the threshold required for even the most efficient C4 plants to survive. The last grasses have withered. The continents of Pangaea Proxima, baked under a 10% brighter sun, are now landscapes of barren rock, shifting dust, and immense, gleaming salt flats. The foundation of almost all complex terrestrial ecosystems, photosynthesis, has ceased. For the animal kingdom, this is the final, inescapable death knell. The intricate web of life, already simplified by the rising heat and spreading aridity, now unravels completely, not with a sudden cataclysm, but with a slow, grinding and silent famine. Imagine the last herbivores, perhaps descendants of creatures we know adapted over hundreds of millions of years to survive the increasingly harsh conditions. Maybe strange, desert-adapted mammals, reptiles, or even insects, clinging to existence in the dwindling C4 savannas. Now, their food source is gone. Utterly. The plains fall silent. The last herds, perhaps already weakened and struggling for water, face absolute starvation. There are no more leaves to browse, no more grasses to graze, no roots or tubers with enough sustenance to support large bodies. The primary consumers, the vital link between the sun's energy captured by plants and the rest of the food web, vanish. Their extinction is relatively swift, a direct consequence of the botanical collapse. It is a slow, quiet fading away, perhaps marked only by the bleached bones left scattered across the barren land. And with the death of the herbivores, the fate of the carnivores is sealed. The last predators, perhaps highly specialized hunters adapted to the unique fauna of this deep future, now face a world devoid of prey. Their own extinction follows inevitably, perhaps lagging only slightly behind that of their food source. The hunters starve in a world that no longer offers sustenance. The intricate dance of predator and prey, which drove so much of evolution's complexity, ends in a final mutual silence. This collapse ripples through every remaining niche. The scavengers find no carcasses. The insectivores find no insects, as the insects themselves succumb to the loss of plants and the extreme conditions. The entire animal kingdom, built layer by painstaking layer upon the foundation of plant life, simply dismantles itself from the top down. Compounding this catastrophic famine are the relentlessly worsening environmental conditions. The heat continues its oppressive reign, making activity difficult, stressing metabolisms, and requiring ever-increasing amounts of water that no longer exist. The disappearance of the oceans means the hydrological cycle has effectively stopped. There is no rain, no rivers, no lakes, save perhaps for those fleeting hypersaline remnants doomed to vanish. Dehydration becomes a universal, inescapable threat, and the air itself may be changing in ways detrimental to animal life. With photosynthesis having ceased globally, the primary source replenishing atmospheric oxygen is gone. While oxygen is a relatively stable gas and its decline would be incredibly slow, potentially taking millions of years to become critical, the lack of replenishment, combined perhaps with slow geological consumption processes, like the oxidation of surface minerals, means the long-term trend is inevitably downward. Complex animals, with their high metabolic demands for oxygen, face not just starvation and heat stroke, but potentially over immense timescales, a slow creeping asphyxiation as well. The extinction of the animal kingdom, unlike the dramatic mass extinctions of the past triggered by asteroids or volcanoes, is likely a quieter, more protracted affair. It is an extinction driven by systemic failure, the failure of the climate, the failure of the atmosphere, the failure of the primary producers. It is the slow, inevitable consequence of a planet crossing fundamental thresholds of habitability. The sounds of the world fall silent. No calls, no roars, no buzzing wings, no rustling in the undergrowth. The movement ceases. The complex behaviors, the hunting, the migrating, the building of nests, stop. The earth, which had pulsed with animal life for over 500 million years, becomes a realm of profound biological stillness. Only the wind blowing dust across the salt flats and eroding the silent mountains remains. The reign of the animals is over. The planet now belongs entirely to the simplest forms of life, the ones that witnessed the very beginning. The forests are gone. The animals are silent. The vast, intricate machinery of the complex biosphere has ground to a halt, starved of carbon and baked by the relentless heat. But the transformation of Earth's atmosphere, the very air enveloping the planet, continues its slow, inexorable course, driven now not by biological activity, but by its absence and by the planet's changing geological and cosmic state. The next crucial change concerns the most vital gas for animal life: oxygen. For over 2 billion years, since the Great Oxidation Event triggered by cyanobacteria, Earth's atmosphere has been characterized by the presence of abundant free oxygen. This oxygen, constantly replenished by the tireless work of plants and algae through photosynthesis, is the high-energy fuel that enabled the evolution of large, active, complex animals. Its presence is arguably the single most defining chemical signature of our living planet. But now the engine of oxygen production has stopped. With the extinction of C3 and C4 plants, global photosynthesis has effectively ceased. The tiny contribution from lingering microbial mats in hypersaline pools or perhaps chemosynthetic bacteria is negligible on a planetary scale. The planet's green lungs have collapsed, and the constant influx of fresh oxygen into the atmosphere has ended. Oxygen is a highly reactive gas. In our current world, its atmospheric concentration is maintained in a delicate balance between biological production, photosynthesis, and consumption, respiration by animals and microbes, decay of organic matter, and slow geological processes like the oxidation or rusting of minerals. In the world of 1 billion years from now, production has stopped, but consumption continues, albeit perhaps at a slower rate. There are no animals left to breathe the oxygen, but microbial respiration, particularly by organisms decomposing the last remnants of dead plant matter or surviving in subsurface environments, would still consume oxygen. More significantly, slow geological processes continue their relentless work. Exposed rocks, rich in iron and other reduced minerals, react chemically with atmospheric oxygen over immense timescales. Volcanic gases, though greatly diminished with the end of plate tectonics, might still seep out in places, releasing reducing compounds that consume oxygen. And perhaps most importantly, the atmospheric escape process, driven by the sun's heat and the potential loss of the magnetic field, doesn't just target hydrogen. While lighter gases escape more easily, even heavier gases like oxygen can be slowly, gradually stripped away from the uppermost layers of the atmosphere over hundreds of millions of years, particularly without the protection of a robust magnetosphere. The result is inevitable. The atmospheric concentration of free oxygen begins a long, slow, irreversible decline. This is not a sudden suffocation. It is a process likely unfolding over tens, perhaps hundreds, of millions of years after the extinction of plants and animals. The atmosphere holds a vast reservoir of oxygen, and the consumption processes are slow. But the trend is undeniable. Without the constant biological replenishment, the oxygen is slowly being consumed by geology and lost to space. Imagine the air itself thinning, losing its vital spark. The 21% oxygen level that sustains us, which perhaps had already dropped slightly with the initial plant die-offs, continues its gradual descent to 15%, to 10%, perhaps eventually over hundreds of millions more years, approaching near zero levels reminiscent of the Archean eon before the first great oxidation. This decline reinforces the permanence of the extinction of complex life. Even if some hypothetical future event were to somehow moderate the temperature or reintroduce water, the lack of sufficient atmospheric oxygen would present an insurmountable barrier to the re-evolution of animals as we know them. The slow fading of atmospheric oxygen is another quiet marker of the planet's biological death. It is the final dismantling of the unique atmospheric conditions created and maintained by complex life for billions of years. The air itself returns to a more primitive, less energetic state, mirroring the biological regression occurring on the surface. The breath of the planet, sustained for so long by the Green Kingdom, finally, slowly, fades away. The oxygen fades. The breath of complex life has long since departed the silent, dry world. The vibrant tapestry woven over 500 million years by animals and plants has unraveled completely, leaving behind a planet stripped bare, baked by a relentless sun, its oceans mere memories etched in salt. But life in its most fundamental, most ancient form endures. The extinction of the complex eukaryotes, the animals, the plants, the fungi, does not mark the end of biology on Earth. Instead, it marks a profound regression, a return to a state the planet has not known for billions of years. The future Earth belongs once again entirely and unequivocally to the microbes. This is the dawn of the second age of prokaryotes, the bacteria and the archaea, the simple single-celled organisms that originated life on this planet nearly 4 billion years ago, inherit the desolation. They were here before the complexities arose, and they will remain long after they have gone. But these are not just any microbes. The conditions on Earth 1 billion years from now, extreme heat, intense aridity, high salinity in the last vestiges of water, harsh ultraviolet radiation, dwindling oxygen, select fiercely for only the most resilient, the most adaptable, the most extreme forms of microbial life. The inheritors are the extremophiles. Imagine the landscape now. The vast salt flats, gleaming under the harsh sunlight, are perhaps stained in patches with deep reds, oranges and purples. These are not mineral stains alone. They are the pigments of immense colonies of haloarchaea, salt-loving microbes that thrive in brine concentrations lethal to almost everything else. They have perhaps evolved even more sophisticated mechanisms to cope with osmotic stress and radiation damage, forming leathery protective mats across the salt crusts where the faintest trace of moisture might persist, perhaps drawn from the atmosphere itself. Near geothermal hotspots, if any faint warmth still seeps from the planet's cooling interior, or perhaps in deep, saline groundwater reservoirs shielded from the surface inferno, thermophilic bacteria and archaea continue their slow, heat-driven metabolisms. These are organisms whose ancestors perhaps never left the high-temperature environments where life may have first originated near hydrothermal vents. For them, the hot Earth is not a catastrophe, but a return to familiar conditions. Perhaps in the thin, oxygen-poor atmosphere, strange metabolic pathways flourish. Methanogens, perhaps, surviving deep underground, produce methane from the last traces of buried organic matter or geological sources. Sulfate-reducing bacteria might thrive in anoxic brine pockets, creating localized pockets of toxic hydrogen sulfide. The planet's biochemistry reverts to simpler, more ancient cycles, driven by organisms that do not rely on oxygen or complex organic food sources. Photosynthesis, the engine of the old biosphere, is not entirely gone, but it is transformed. Heat-tolerant cyanobacteria, perhaps related to those that triggered the first oxidation event billions of years earlier, might form dark, crusty mats in the few locations where minimal moisture and sunlight allow, performing a slow, struggling version of oxygenic photosynthesis, or perhaps reverting to simpler, anoxygenic forms that do not produce oxygen at all. Life exists, but it is life stripped down to its bare essentials. It is life focused solely on survival, on enduring the immense physical and chemical stresses of the environment. The rapid evolution, the diversification, the complex interactions that characterized the Phanerozoic eon are likely gone. In this energy-poor, resource-limited world, microbial evolution itself may slow dramatically. The remaining organisms, perfectly adapted to their extreme niches, might persist almost unchanged for hundreds of millions, perhaps billions, of years. The Earth has become a microbial planet once more, but it is not the vibrant, globally interconnected microbial world of the Archean, teeming with potential. It is a depleted, fragmented and stressed microbial world, clinging to existence in isolated pockets of marginal habitability on a planet that is slowly, irrevocably dying. The complex experiment of multicellular life has ended. The long, quiet and incredibly resilient reign of the extremophiles is the final, enduring biological chapter of Earth's story. The surface world belongs to the extremophiles, the hardy microbes painting the salt flats and enduring the searing heat. But even these resilient surface communities exist on borrowed time, exposed to the full, intensifying fury of the sun and the desiccating atmosphere. As the conditions become ever more extreme, the last truly viable sanctuaries for life on Earth lie hidden, shielded from the planetary inferno. Life retreats into the final, deepest pockets of marginal habitability. One major refuge lies beneath the surface, deep within the rock crust of Pangaea Proxima. We must remember that the Earth's crust is not a solid, impermeable shell. It is fractured, porous, permeated by networks of tiny cracks and fissures, and potentially containing vast, ancient reservoirs of groundwater trapped kilometers below the surface. Imagine descending into this subterranean realm. Here, shielded by thousands of meters of rock, the conditions are dramatically different from the surface. The crushing heat of the sun does not penetrate. The lethal ultraviolet radiation is completely blocked. The extreme daily or seasonal temperature swings are smoothed out into a near constant, albeit potentially still very warm, ambient temperature dictated by the planet's slow internal cooling. And crucially, liquid water may persist here long after the surface oceans have vanished. While surface evaporation is relentless, deep groundwater, isolated from the atmosphere, might remain trapped within rock formations for hundreds of millions, perhaps billions of years. This water would likely be ancient, incredibly salty, perhaps chemically strange, laden with minerals leached from the surrounding rock over eons. But it would be liquid. In these dark, stable, potentially water-bearing subterranean environments, life could endure, entirely decoupled from the surface world. This would be a kingdom of chemosynthesis. Microbes, bacteria and archaea would draw energy not from sunlight, but from slow chemical reactions involving the minerals in the rock and dissolved gases seeping up from deeper within the earth. Organisms that eat hydrogen, methane, sulfur or iron, extracting the faint chemical energy released by inorganic reactions. These deep subsurface ecosystems, known collectively as the deep biosphere, exist on Earth today, extending kilometers down into the crust. In the far future, this hidden realm may become the only significant biosphere left. Life would return entirely to the darkness, mirroring its potential origins near deep-sea hydrothermal vents, sustained by the planet's faint, lingering geological and chemical whispers, rather than the sun's overwhelming fire. Another potential, though perhaps more temporary sanctuary might exist near the poles. While the average global temperature soars, the poles, receiving sunlight at a much lower angle, would remain the relatively coolest parts of the planet. While certainly not cold by our standards, they might lag behind the equatorial regions in reaching truly lethal temperatures. Could simple microbial life, perhaps photosynthetic cyanobacteria adapted to high temperatures and salinity, cling to existence in damp patches near the poles, perhaps fed by the slow melting of any remaining subsurface ice or permafrost? It is a possibility, at least for a time. Imagine the stark, eroded polar landscapes of Pangaea Proxima, perhaps harboring faint, dark crusts of microbial life in the most sheltered, shaded or slightly moist locations. These polar oases, however, would be fighting a losing battle against the steadily increasing solar luminosity. Eventually, even the poles would become too hot and dry to sustain any surface life relying, even indirectly, on lingering ice or atmospheric moisture. Ultimately, the deep subsurface remains the most probable final bastion. Life, born perhaps near the surface or in shallow vents, completes its planetary journey by retreating back into the rock from which the planet itself was formed. These final sanctuaries, deep rock fissures, ancient saline aquifers, perhaps geothermal pockets, would be isolated, fragmented islands of biology in an otherwise sterile world. Evolution within them might slow to an almost imperceptible crawl, the organisms within simply enduring, unchanging, for timescales that dwarf the entire history of complex life. They are the last embers, glowing faintly in the deep geological darkness long after the surface fire has consumed everything else. As Earth submits to the relentless heat, its oceans vanishing, its complex life extinguished, our gaze might naturally turn outwards, seeking perhaps a reflection, a comparison, or even a desperate hope in our nearest planetary neighbor, Mars, the red planet. In our own time, it represents the frontier, the tantalizing possibility of finding past or even present life beyond Earth, the potential future refuge for humanity. But in the deep future of 1 billion years from now, what becomes of Mars as Earth itself transforms into a scorching, sterile world? Mars orbits farther from the Sun than Earth. This greater distance means it receives significantly less solar energy. While the 10% increase in the Sun's luminosity spells doom for Earth, for Mars, it represents a different kind of change, a slow, gentle warming. Imagine the Martian landscape in this distant future. It is still cold by Earth standards, still a world of thin atmosphere and rusty dust. But the relentless increase in solar output might raise its average temperature slightly, perhaps enough to sublimate some of the frozen carbon dioxide ice caps, or even melt pockets of subsurface water ice, creating fleeting, localized environments slightly less hostile than they are today. Could Mars, paradoxically, become more habitable as Earth becomes less so? Could this faint warming provide a temporary, marginal window for any hypothetical Martian microbial life, dormant beneath the surface, to stir? It is a fascinating, though highly speculative thought. However, Mars faces its own profound, long-term challenges that likely preclude it from ever becoming a true haven as Earth dies. Mars is a smaller planet than Earth, with significantly weaker gravity. Billions of years ago, it lost its global magnetic field, leaving its atmosphere vulnerable to stripping by the solar wind. Over eons, its once thicker, perhaps warmer and wetter atmosphere has thinned dramatically, bled away into space. While the increased solar warmth might temporarily boost surface temperatures, it does nothing to restore Mars's lost atmosphere or its absent magnetic shield. In fact, the intensifying solar wind emanating from the hotter sun might even accelerate the atmospheric stripping process on Mars, counteracting some of the warming effects. Mars, 1 billion years from now, is likely still a cold, dry, and radiation-bathed world. Perhaps slightly less frigid than today, perhaps with slightly more active sublimation cycles near its poles, but fundamentally still a planet whose own window of potential surface habitability closed billions of years in the past. It offers no true refuge. The relationship between the two planets also changes on a cosmic scale. As we noted, the orbits of the inner planets are chaotic over vast timescales. While a direct collision is exceedingly unlikely within the next billion years, the relative positions and orbital resonances between Earth and Mars will shift unpredictably. The closest approaches, the optimal windows for theoretical travel between the worlds, will change. The precise gravitational dance between the two neighbors evolves. Mars, in the deep future, serves not as a lifeboat, but perhaps as a ghostly mirror. It reflects a potential past, a world that may once have held water and perhaps life, but lost it. And it reflects a potential, though different, future, a world succumbing to atmospheric loss and stellar radiation. Watching Earth bake and Mars remain cold and thin underscores the delicate, perhaps unique balance of factors that allowed complex life to flourish here for so long. The illusion of Mars as a future home fades against the harsh realities of planetary evolution and stellar physics. It remains a silent, red witness to Earth's slow demise, following its own separate path towards cosmic silence. As Earth slowly follows its inevitable path towards becoming a hot, dry, and sterile world, our gaze shifts inwards towards our other planetary neighbor, the second planet from the Sun, Venus. In the scorching future of 1 billion years from now, Venus serves not as a potential refuge like Mars, nor merely as a silent witness, but as a terrifying ghost of Earth's own destiny, a stark reminder that this catastrophic transformation has happened before in our own solar system. Venus today is the definition of a planetary hellscape. Its surface temperature is a staggering 460 degrees Celsius, hot enough to melt lead. Its atmosphere is incredibly dense, 90 times the pressure of Earth's, composed almost entirely of carbon dioxide, laced with clouds of corrosive sulfuric acid. It is a world crushed, choked, and utterly sterilized by a runaway greenhouse effect far more extreme than the one beginning to grip the future Earth. But Venus was not always this way. Scientific models and indirect evidence suggest that early in the solar system's history, billions of years ago, when the young sun was significantly fainter, Venus may have been a very different world. It might have possessed liquid water oceans on its surface. It might have had a thinner atmosphere, perhaps even temperate conditions. For a time, Venus might have been habitable, potentially even harboring the first sparks of simple life. What went wrong? Venus orbits closer to the Sun than Earth. As the young sun slowly began its inexorable brightening, Venus reached the critical threshold for a runaway greenhouse effect much, much earlier than Earth ever will. Imagine early Venus, perhaps a blue world with shallow seas. As the sun's output increased, its oceans began to evaporate faster, pumping more water vapor into its atmosphere. Water vapor trapped heat, raising the temperature, causing more evaporation, the same deadly feedback loop that will eventually consume Earth's oceans. But on Venus, being closer to the Sun, this process likely reached a tipping point far more quickly and violently. Its oceans boiled away entirely, perhaps within a relatively short geological span. The immense amount of water vapor in the atmosphere was then broken apart by solar ultraviolet radiation, and the lighter hydrogen escaped into space, just as it will from Earth's future atmosphere. Venus lost its water permanently. Without oceans to dissolve carbon dioxide or plate tectonics, which may have stopped early on Venus, or perhaps never fully started in an Earth-like way, to recycle carbon back into the mantle, the vast quantities of carbon dioxide released by volcanic activity simply accumulated in the atmosphere. The greenhouse effect spiraled completely out of control, leading to the crushing, infernal conditions we see today. Venus is the ghost of Earth's future. It is a planetary cautionary tale written large in the inner solar system. It shows, with brutal clarity, the ultimate fate of a rocky planet orbiting too close to a brightening star. 1 billion years from now, as Earth's oceans evaporate under the 10% brighter sun, as its atmosphere thickens with water vapor before being stripped away, as its surface temperature climbs towards lethal levels, it will be treading the same path that Venus walked billions of years before. Earth's greater distance from the Sun granted it a much longer period of habitability, a grace period of billions of years. But the fundamental physics are the same. The end state, driven by the inescapable stellar evolution, is tragically similar. Looking towards Venus in that deep future sky, a Venus that will itself likely be even hotter, its thick atmosphere perhaps undergoing further chemical changes under the intensifying solar radiation, will be like looking into a distorted mirror, reflecting Earth's own inevitable, scorching destiny. The sister planets, perhaps once similar in their youth, ultimately diverge, one succumbing early to the star's fire, the other granted a longer, blue middle age, before finally following the same path towards becoming a silent, cloud-shrouded kiln world. Venus's ghost haunts the future Earth, a constant reminder of the fragility of habitability and the relentless power of the star we orbit. While the cosmic neighbors follow their own distant destinies, and the Sun relentlessly dictates the planet's thermal future, the Earth itself settles into its final, grand geographical configuration. The slow dance of the continents, driven by the last embers of mantle convection, reaches its ultimate conclusion, the assembly of Pangaea Proxima. This final supercontinent, born from the closure of today's oceans, defines the physical stage upon which the last acts of Earth's habitability play out. Let us try to visualize this world, perhaps 250 million years from now, before the oceans have completely vanished, but after the continents have locked into place. The map is utterly transformed. The familiar shapes of the Atlantic, the Indian, the Arctic oceans are gone, squeezed out of existence by the converging land masses. Africa sits at the heart of the New World, having collided firmly with Europe to the north, North America to the west, and South America wrapping around its southern edge. Antarctica and Australia have likely joined the southern margin of this colossal assembly. What remains of the oceans? The vast Pacific, the direct descendant of the ancient Panthalassa, has become even larger, a true super ocean covering perhaps 2/3 of the planet's surface, surrounding Pangaea Proxima on all sides. Within the heart of the supercontinent, perhaps trapped near the equator where India, Africa and Eurasia meet, might lie a smaller, isolated and likely very warm, saline inland sea. The last remnant of the Indian Ocean, or the ancient Tethys. This geographical arrangement, a single massive landmass surrounded by a single super-ocean, recreates, in a sense, the conditions of the original Pangaea, but with crucial differences dictated by the specific geometry and the relentless solar warming. Pangaea Proxima is likely centered more equatorially than its predecessor. This concentration of land in the warmest latitudes exacerbates the planetary heating. The sheer size of the landmass leads once again to extreme continentality. Imagine the interior of Pangaea Proxima, thousands upon thousands of kilometers from the moderating influence of the Super-Pacific. It becomes a new, colossal, hyper-arid desert, perhaps even larger and hotter than the desert heart of the original Pangaea, baked relentlessly under the significantly brighter sun. Temperatures here could reach unimaginable extremes, the land utterly sterile, scoured by dry winds carrying dust across the silent, empty plains. The coastlines, though extensive, face the immense fetch of the Super-Pacific. Weather patterns would be dominated by immense, perhaps permanent, high and low pressure systems generated by the temperature contrast between the superheated land and the vast ocean. Coastal regions might experience extreme, though perhaps infrequent and geographically concentrated, mega monsoons, or conversely be locked in perpetual coastal deserts depending on prevailing wind patterns. And the mountains, the collision zones that welded Pangaea Proxima together, stand as immense, young, geologically speaking, mountain ranges. A colossal chain runs along the seam where the Americas met Africa and Europe, the final scar of the closed Atlantic. Another immense range marks the final closure of the Tethys/Indian Ocean remnants between Africa, India and Eurasia. These mountains, potentially far higher than the modern Himalayas, would dramatically influence atmospheric circulation, blocking moisture, creating rain shadows, and further contributing to the extreme climate patterns across the supercontinent. This final geographic configuration sets the stage for the last phase of Earth's habitability. The concentration of land, the vast interior desert, the altered ocean circulation all interact with the increasing solar luminosity to accelerate the planet's demise. Pangaea Proxima is not just the final arrangement of the continents. It is the geographical framework within which the oceans will evaporate, complex life will vanish, and the planet will settle into its long, final silence. It is the last map of a dying world. The Grand Assembly is complete. Pangaea Proxima stands as the Earth's final continental configuration, a vast unified landmass forged from the slow collision of the world we know. But the birth of this supercontinent involved the death of oceans, the final closing chapters for vast bodies of water that once defined our planet's geography. Let us linger for a moment on the memory of these closing seas and the monumental geological scars they left behind. Consider first the Atlantic Ocean. Born from the initial rifting of the original Pangaea, it widened for over 200 million years, separating the Americas from Africa and Europe, growing into a mature deep ocean basin defined by its immense mid-ocean ridge. But its fate was sealed by the relentless engine of plate tectonics. New subduction zones formed along its western margins, beneath the eastern coasts of North and South America. Imagine this process in slow motion. The cold, dense oceanic crust of the Atlantic floor began to plunge back into the Earth's mantle beneath the overriding American continents. This relentless downward pull acted like a cosmic anchor, slowly, inexorably dragging the Americas eastward, back towards Africa and Europe. Millimeter by millimeter, century by century, the Atlantic Ocean began to shrink. The vast expanse of water narrowed. Islands' arcs, perhaps resembling the modern Caribbean or Indonesian archipelagos, might have formed above the subduction zones, volcanic chains born from the melting of the descending oceanic plate. But the overall trend was one of closure. The final moments, geologically speaking, would have been dramatic. The last sliver of the Atlantic Ocean floor, including the mid-ocean ridge itself, dives beneath the Americas. The continents, floating on their tectonic plates, make final contact. Africa collides with North America. South America nestles against the bulge of Western Africa. The impact zone is a region of immense geological violence, sustained over millions of years. The continental crust buckles, folds, and fractures. Sheets of rock are thrust upwards, piling atop one another. The remnants of the island arcs, the sediments that filled the final Atlantic seaway, the ancient continental margins themselves, all are caught in this colossal vice. The result is the mountain range we envisioned earlier, a new, immense chain stretching potentially for thousands of kilometers along the suture line, perhaps from the Arctic down past the equator. Imagine peaks rising higher than the Himalayas, born from the death of an ocean. This colossal range stands as the final tombstone of the Atlantic, a monumental scar marking where two worlds, once separated by a vast sea, became one again. A similar, though perhaps more complex drama unfolds further east, sealing the fate of the last remnants of the ancient Tethys Ocean, our modern Mediterranean Sea, and perhaps parts of the Indian Ocean. Africa's relentless northward push into Eurasia continues, squeezing these remaining water bodies. Islands are crushed against the mainland. The sea floor is subducted. The collision intensifies. This creates the other great mountain system of Pangaea Proxima, that immense chain running east-west across the heart of the supercontinent, extending the Alps, folding through the Middle East, and potentially linking with the remnants of the Himalayas formed by India's earlier collision. Another ocean vanishes, replaced by towering peaks. The closure of these oceans represents the final act of large-scale plate convergence on Earth. It eliminates the last major seaways that allowed for global ocean circulation patterns similar to our own. It welds the continents into their final, inescapable configuration, and it creates the last great mountain ranges the planet will ever see. These ranges, born from the death throes of oceans, will stand as the dominant features of Pangaea Proxima's landscape, immense silent monuments to the final consolidation of the Earth's crust, just before the geological engine that built them finally falls silent forever. The oceans have closed. The final colossal mountain ranges stand sentinel over the unified landmass of Pangaea Proxima. The continents, after billions of years of restless wandering, have finally come together in their ultimate configuration. And now, as the planet's internal heat continues its slow fade, the very engine that drove this epic journey, plate tectonics, grinds to its final, irreversible halt. The continents are sealed in place, their positions now permanent on geological timescales. Imagine the profound stillness that descends upon the Earth's crust. The immense, slow friction between colliding plates ceases. The deep, unseen creep of continents across the mantle stops. The subtle rising and falling of land masses in response to deeper currents ends. For the first time since the very early days of the planet, perhaps since the crust first solidified, the surface becomes essentially static. This geological stasis locks the geography of Pangaea Proxima into its final, enduring form. The immense mountain ranges, freshly raised by the closure of the Atlantic and Tethys remnants, will never grow higher. The vast interior basins will never deepen through tectonic subsidence. The coastlines, now defined by the edge of the Super-Pacific and perhaps the shores of a shrinking inland sea, will no longer migrate due to continental drift. The map is fixed. But the cessation of plate tectonics does more than just freeze the geography. It seals the fate of the landscape itself by shutting down the great geological recycling system. Without the constant creation of new crust at mid-ocean ridges, and the destruction of old crust at subduction zones, the rock cycle slows dramatically. Without the uplift associated with mountain building, the primary force that exposes fresh rock to the surface for erosion is removed. Initially, the existing mountains, towering and immense, will still be subject to weathering and erosion. But even these processes will falter and change profoundly in the hot, dry world of the future. Chemical weathering, the breakdown of rocks by water and atmospheric gases, becomes incredibly slow without abundant liquid water and with the atmosphere depleted of carbon dioxide. Physical weathering, the breakdown of rocks by temperature changes, wind abrasion, and perhaps salt crystallization, continues, but its effects are different. Imagine the wind, the only remaining significant agent of surface change, scouring the high peaks, carrying dust and sand across the immense arid plains. Slowly, patiently, over hundreds of millions of years, the mountains will erode. But without the constant geological uplift to counteract this erosion, and without the powerful action of rivers and glaciers, which require water, the process is incredibly slow, perhaps grinding down the colossal ranges millimeter by millennium. Furthermore, the sediments produced by this slow erosion have nowhere to go in a geological sense. With no active subduction zones to carry them back down into the mantle, they simply accumulate in the vast interior basins of Pangaea Proxima, or perhaps are blown out into the remaining super-ocean, gradually shallowing its edges. The planet's surface becomes increasingly dominated by vast, ancient, eroded landscapes and thick accumulations of static sediment. This permanent geological seal locks the planet into a state of profound inactivity. It is the Earth settling into its final old age. The dynamic, creative and destructive forces that shaped its surface for billions of years are spent. What remains is a world preserved in stone, a static monument to its fiery past, its features changing now only at an almost imperceptibly slow pace under the relentless glare of the brightening sun and the dry whisper of the wind. The continent's permanent seal marks the true end of Earth's geological youth and the beginning of its long, slow, final decline towards becoming an inert, unchanging sphere. The continents are sealed. Pangaea Proxima stands immutable, its final form dictated by the last gasps of tectonic collision. The planet's internal heat engine has sputtered and died, leaving the crust locked in a permanent, motionless embrace. Now a profound silence descends upon the Earth, a silence deeper than any ocean, more enduring than any mountain range. This is the silence of geological death. Imagine a world without the faintest tremor beneath your feet. For billions of years, the Earth's crust has been a dynamic, fractured entity, constantly adjusting, grinding, and releasing stress in the form of earthquakes. From the smallest imperceptible shifts to the catastrophic ruptures that reshape landscapes, seismic activity has been a constant hum beneath the surface noise of life. But now, with the tectonic plates fused and motionless, the sources of this stress are gone. The great fault lines that defined the plate boundaries, the zones where continents scraped past each other or dove beneath one another, become inactive scars. The slow buildup of strain within the rock ceases. Earthquakes, the sudden, violent exhalations of a stressed planet, simply stop. The ground becomes utterly, permanently still. Imagine a world without the fiery breath of volcanoes. Volcanism, in its many forms, is a direct consequence of the planet's internal heat and the movement of its crust. It occurs where plates pull apart, allowing magma to rise from the mantle. It occurs where plates collide, forcing water-laden crust down into the hot depths, causing rock to melt. It occurs where plumes of superheated material rise from the deep mantle, punching through the crust to form islands like Hawaii. But now, the engine driving these processes is cold. The mantle is sluggish, perhaps solidifying in its upper layers. Subduction has ceased. Rifting has stopped. The pathways for magma to reach the surface are closed off. The great volcanic chains, the Andes, the Cascades, the fiery arcs of the Pacific Ring of Fire, fall permanently dormant. The mid-ocean ridges are cold, dead scars on the floor of the vanished oceans. Even the persistent hotspot volcanoes eventually exhaust their deep heat source and fade away. The planet stops building new land. It stops releasing its internal gases. The fire within is extinguished. Imagine a world where mountains only shrink, never grow. Mountain ranges are born from the immense power of tectonic collisions, the crust buckling and uplifting under unimaginable pressure. This process, which raised the Himalayas, the Alps, and the final colossal ranges of Pangaea Proxima, requires moving plates. With the continents locked in place, mountain building ceases entirely. The existing ranges, towering monuments to the planet's dynamic past, now face only the slow, relentless forces of erosion, the dry wind, the thermal expansion and contraction of rock under the intense solar heating. Millimeter by millennium, they are worn down, their sharp peaks softening, their immense height gradually diminishing over hundreds of millions, perhaps billions, of years. But no new mountains rise to replace them. The planet's surface relief, the dramatic contrast between high peaks and low basins, begins a slow, final journey towards flatness. This lasting geological silence is more than just the absence of dramatic events. It signifies the end of the Earth as a dynamic, self-regulating system. The processes that recycled crust, replenished the atmosphere, created diverse landscapes, and drove mineral cycles have stopped. The planet becomes a passive entity. Its surface features now merely subject to the slow decay imposed by external forces, the intensifying sun, the faint whisper of atmospheric erosion. It is a profound stillness, a geological quietus settling over the entire globe. The Earth, once a vibrant, churning, ever-changing sphere, enters its final, long phase as an inert ball of rock, its surface features preserved like ancient monuments under the harsh, unwavering light of its aging star. The silence is absolute, broken only by the sound of the wind blowing across a world that no longer moves from within. The geological silence has fallen. The continents of Pangaea Proxima stand locked and still, their final mountain ranges slowly yielding to the patient abrasion of the wind. The Earth's internal fire is extinguished, but the external fire, the relentless, intensifying blaze of the sun, continues its cosmic mandate. We now push our journey slightly further into the deep future, past the 1 billion year mark, perhaps to 1.2 billion years from now. This is the time frame within which the final act of the planet's hydrological drama unfolds. The last vestiges of the oceans complete their slow, inevitable journey into the void. Imagine the sun now. Its luminosity has continued to climb beyond that critical 10% threshold. It might now be 20, perhaps even 25 or 30% brighter than the star we know today. The energy pouring onto the dry, static Earth is immense, inescapable. The surface temperature, already far beyond the boiling point of water under normal pressures, continues its ascent. The vast salt flats, remnants of the evaporated seas, bake and perhaps even begin to melt or deform under the extreme, sustained heat. The ancient rocks of the continents expand, crack, and weather under thermal stress unlike anything in their long history. And the last traces of water, they are relentlessly hunted down and destroyed. Remember the atmospheric escape process, water vapor rising high, broken apart by ultraviolet light, the hydrogen bleeding into space. This process, which began with the moist greenhouse, continues as long as there is any significant water vapor left in the atmosphere. The hotter sun accelerates this process dramatically. Its increased ultraviolet output acts like an even sharper knife, dissociating water molecules more efficiently. The higher atmospheric temperatures give the escaping hydrogen atoms even greater velocity, ensuring their departure. Any water trapped deep underground, perhaps in ancient aquifers shielded from the initial surface evaporation, is slowly driven out by the increasing geothermal gradient as the planet's surface heats. This water vapor eventually finds its way to the upper atmosphere and is lost. Water chemically bound within certain minerals in the crust might be liberated by the intense heat, adding minuscule amounts to the atmospheric inventory, only to be promptly destroyed and lost as well. This is the final, complete desiccation. Sometime around this 1.2 billion year time frame, the models predict the very last significant reservoirs of water within the Earth system accessible to the atmosphere are exhausted. The atmospheric escape process, having consumed entire oceans, finally runs out of fuel. The planet becomes truly, profoundly dry. Not just arid, not just desert-like, but dry in a fundamental, chemical sense, perhaps drier than the Moon is today. The atmosphere itself transforms. Without the constant influx of water vapor, it likely becomes thinner still, though perhaps dominated now by heavier gases like nitrogen and any remaining oxygen or carbon dioxide that haven't been stripped away or locked into minerals. It remains incredibly hot, a dense, dry, heat-trapping blanket, but one devoid of the familiar humidity that characterized the moist greenhouse phase. The Earth, 1.2 billion years from now, has reached its final environmental state under a still evolving sun, before the red giant phase much later. It is a static, geologically dead supercontinent, Pangaea Proxima, surrounded perhaps by vast, incredibly ancient, wind-eroded salt plains where oceans once churned. It is bathed in intense heat and lethal radiation from a significantly brighter star. Its atmosphere is thin, dry, and hostile. Liquid water, the essential solvent for life as we know it, is entirely, permanently absent from the surface, and likely from all but the deepest, most isolated pockets within the crust. This is the ultimate landscape of the deep future Earth, a silent red and white world, orbiting a star that has become too bright, too hot for the gentle chemistry of life. The long, vibrant 4 billion year story of Earth as a habitable planet has definitively ended. What remains is simply a matter of stellar physics and the slow decay towards the Sun's final transformative stages, billions of years further down the line. The oceans are gone, not just receded, not just hypersaline remnants, but utterly vanished from the surface of the Earth, their water dismantled and lost to the cosmos. The planet, approximately 1.2 billion years from now, has achieved its final state of profound, irreversible dryness. What remains is a world sculpted by heat, time, and absence. Let us linger for a moment in this ultimate landscape, the enduring face of the deep future Earth. The geography is locked. The single vast supercontinent of Pangaea Proxima, perhaps cracked and weathered by thermal stress but geologically inert, covers a significant portion of the globe. Its immense ancient mountain ranges, born from the final continental collisions, stand silent and colossal, though perhaps noticeably eroded by billions of years of wind abrasion. Their peaks possibly softened, their slopes buried in deep drifts of fine, dry dust and sand. Surrounding this supercontinent, where the abyssal plains of the Pacific and other oceans once lay, stretch the great global salt pans. These are no longer gleaming white, perhaps. Over hundreds of millions of years under the intense solar radiation and bombarded by cosmic rays, the pure salt crystals may have undergone chemical changes, perhaps taking on duller, reddish or brownish hues due to impurities baked in by the heat or radiation damage. They remain vast, incredibly flat, broken only by wind-carved ridges or perhaps the strange, slow, crystalline flow of the salt itself under immense, sustained heat and pressure. There are no rivers, no lakes, no glaciers, no frost. The hydrological cycle, the constant movement of water between atmosphere, land and sea that defines our living world, has completely ceased. The primary agent of erosion and change is now the wind. Imagine a thin, hot, dry atmosphere, perhaps composed mainly of nitrogen and residual oxygen or carbon dioxide, perpetually in motion due to the extreme temperature differences between the sunlit and shadowed sides of the slowly rotating planet, or between the equator and the poles. This wind carries fine dust stripped from the ancient mountains and perhaps microscopic salt crystals lifted from the Great Plains. It is a constant, abrasive whisper across a silent world. The sun hangs in this sky, visibly larger, significantly brighter, perhaps appearing almost white-hot rather than the familiar yellow. Its energy output continues its slow climb towards the red giant phase billions of years further on. The light it casts is harsh, unfiltered by ozone, bathing the surface in lethal levels of ultraviolet radiation. The surface temperature is extreme, a stable global average far exceeding the boiling point of water. The rocks themselves are baked, perhaps exhibiting strange metamorphic textures from the prolonged intense heat. The daily cycle is one of scorching heat under the direct sun, followed by a slightly less scorching but still incredibly hot night as the thin, dry atmosphere retains the day's thermal load. And life persists only in its most hidden, most tenacious forms. Deep within the crust, kilometers below the surface, shielded from the heat and radiation, perhaps within pockets of ancient, trapped, geochemically sustained water, extremophile microbes, the deep biosphere, continue their incredibly slow, anaerobic existence. They are utterly disconnected from the surface, drawing energy from faint chemical gradients in the rock, living fossils of a 4 billion-year-old rock biological history, waiting in a darkness that will never end. The surface itself is sterile, a monument to physics overwhelming biology. This is the enduring state of the Earth for perhaps the next several billion years. A dry, hot, geologically dead, microbially sparse, radiation-baked rock. It is the final, stable configuration before the Sun itself enters its last, transformative stages. The vibrant, dynamic, blue-green world is a distant, almost unimaginable memory. What is left is simply stone, salt, heat, and silence. The world is dry, utterly, permanently dry. The sun, significantly brighter now, beats down relentlessly on the static salt-encrusted landscape of Pangaea Proxima. Life clings on only in the deepest subterranean refuges, a faint microbial echo of a biosphere long since vanished from the surface. This state of profound desolation is not a temporary phase. It is the enduring reality of the Earth for billions of years to come. Let us contemplate the passage of time in this final, silent era. The planet continues its slow, slightly longer rotation around the intensifying sun. The moon continues its patient outward spiral. The geography remains locked, unchanging, save for the almost imperceptibly slow erosion by the hot, dry wind. Imagine the nights on this future Earth. The sun dips below the horizon, perhaps casting long, stark shadows across the immense salt flats and the ancient, worn-down mountains. But the darkness brings little relief. The thin, dry atmosphere, though poor at distributing heat, still retains a significant portion of the day's immense thermal load. The rocks themselves hold the heat, radiating it back slowly through the long night. The nights are not cool, they are merely less scorching than the days. A profound, unwavering heat persists, a constant reminder of the star's dominance. The silence is absolute. No crickets chirp, no nocturnal predators stir, no leaves rustle in a non-existent breeze carrying the scent of moisture. There is only the vast, empty stillness of a planet whose complex life has ended. Think of the sheer number of these nights, billions upon billions of them, stretching forward through unimaginable eons. Sunrises paint the Kerzal landscapes, days bake under the intense solar glare, sunsets fade into the deep, star-filled, though perhaps subtly shifted, sky, and the long, hot nights pass in utter silence. The rhythm is simple, stark, and unchanging. The only life aware of this endless cycle exists kilometers below in the dark, isolated pockets of the deep biosphere. These ancient microbes, locked in their subterranean world, have no concept of day or night, no awareness of the sun's fire or the moon's distant dance. They simply endure, their metabolisms running at an incredibly slow pace, perhaps dividing only once every 1,000 years, their existence measured not by seasons or years, but by geological epochs. They are the final, almost eternal heartbeats of Earth's long biological story, beating faintly in the planet's deep, rocky chest. On the surface, there is only geology and astronomy playing out their final, slow acts. The wind moves dust. The rock slowly wears away. The sun continues its steady, inevitable climb towards the red giant phase, still billions of years away, but casting an ever longer, ever hotter shadow over the world it once nurtured. These last nights of Earth as a rocky planet, before the sun's final expansion engulfs it, are nights of profound peace, perhaps, but also of ultimate solitude. It is the quiet ending that awaits worlds where the delicate balance of habitability is finally, irrevocably broken. A long, slow fade into the cosmic background, marked only by the silent passage of innumerable, identical starlit nights over a world that sleeps a final, geological sleep. And so our journey into the deep future reaches its silent conclusion. We have traveled 1 billion years forward in time, witnessing the slow, inexorable transformation of our vibrant blue planet into a dry, static, and profoundly silent world. We have seen the sun, our life-giving star, begin its slow betrayal, driving the oceans to boil and escape into the cosmic void. We watched as the green kingdom withered, starved of the very air it needed, and as the animal kingdom followed, leaving the stage to the resilient reign of the microbial extremophiles. We felt the planet's internal geological heart slow and finally cease its beating, locking the continents into their final embrace as Pangaea Proxima, a silent monument under a harsh sky. The story of Earth's far future, as understood through the lens of physics and geology, is one of profound, inescapable change. It is a humbling reminder that the conditions that allow for complex life, for oceans of liquid water, for breathable air, are not permanent features of this planet. They are a delicate balance, a temporary window of opportunity in the vast sweep of cosmic time. Our world, teeming with life, noisy with activity, constantly reshaped by water and wind and internal fire, is a fleeting exception, not the eternal rule. The deep future reveals the ultimate, underlying simplicity towards which planetary systems tend: stillness, dryness, silence. Yet, to contemplate this immense timescale, this slow unwinding of a habitable world, is not necessarily an exercise in despair. It is an exercise in perspective. The sheer vastness of the future, like the deep abyss of the past we often explore, dwarfs the scale of our own concerns, our own fleeting moments. To stand in imagination on the silent, sun-baked salt flats of the future Earth, under a sky devoid of clouds, is to appreciate, perhaps more profoundly, the miracle of the present. The coolness of a gentle rain, the sound of waves on a shore, the rustle of leaves in a forest, the simple act of drawing a breath of oxygen-rich air. These are the transient gifts of a planet in its vibrant middle age. The journey we have taken tonight shows us that even worlds eventually grow old and die. But it also shows the immense, almost unimaginable duration of stability that allowed life to arise, to evolve, to diversify into the wondrous complexity we see around us and within us. The 1 billion years leading to this desolation were preceded by nearly 4 billion years of dynamic, often chaotic, but ultimately life-sustaining history. The future silence echoes the deep silence of the planet's beginning, bookending the long, extraordinary story of Earth's life. And perhaps now, as you let your mind gently release these images of the far future, as you return your awareness to the quiet stillness of your own present moment, you can carry with you that sense of deep time. Feel the vast, slow rhythm of the cosmos, the rise and fall of worlds, the patient unfolding of billions of years. Let the sheer scale of it diminish the sharp edges of today's worries. The Earth, 1 billion years from now, will be a silent testament to cosmic forces, but tonight, here, now, it is still blue, still alive, still turning. The sun is still a gentle warmth, not a consuming fire. The oceans still hold their deep, mysterious life. The air still carries the breath of forests. Allow the silence of that deep future to merge with the quiet of your room. Allow the stillness of that geologically dead world to deepen your own sense of peace, your own relaxation. The journey is over. The future, in its own time, will unfold. But now is the time for rest. Let the vastness carry you, gently, peacefully, into the quiet harbor of sleep. The echoes of the deep future fade. The image of a silent, dry Earth orbiting its brightening star dissolves into the quiet darkness. Our voyage across 1 billion years has reached its end, returning us gently to the present moment, to the stillness of this room, to the edge of sleep. We have journeyed through unimaginable timescales, witnessing the slow, grand, and inevitable transformations driven by the laws of physics that govern stars and planets. We saw the oceans yield to the sun's growing fire, The continents lock into their final embrace, and the vibrant pulse of complex life falls silent, leaving only the faintest microbial whispers in the deep rock. It is a story of profound change, a humbling perspective on the fragility of our world and the preciousness of this fleeting moment of habitability. But it is also a story written on a scale so vast, so far removed from our immediate concerns, that it invites a sense of peace, a letting go. The distant future holds its own destiny, unfolding at a pace beyond our comprehension. What matters now is only the gentle rhythm of your own breath, the feeling of quiet comfort, the slow, welcome drift towards rest. Let the vastness of deep time be a calming presence, a reminder of the slow, enduring cycles of the cosmos, a backdrop against which your own mind can find stillness. The silence of that future Earth merges now with the quiet surrounding you. The heat of that distant sun fades into the gentle warmth of your own rest. The journey is complete, the story is told, and now there is only the peaceful, quiet, and welcoming embrace of sleep. Allow yourself to drift. Allow the silence to deepen. Rest now. Good night.